Section 3.6 is marginals, differentials, and linearization. And a lot of this is going to seem somewhat familiar to you because if you will recall from taking algebra, oftentimes you were asked to find the slope of a line given 2 points. And this activity, or this lesson rather, will probably bring to mind some of that as we go through the topics in this section. I'm going to start off by looking at a few definitions here. Let C of x, R of x, and P of x represent, respectively, the total cost, total revenue, and total profit from the production and sale of x items. The marginal cost at x, given by C prime of x, is the approximate cost of the x plus first, x plus once item, I guess it should say. C prime of x is approximately equal to C of x plus 1 minus C of x, or C of x plus 1 is approximately C of x plus C prime of x. The marginal revenue at x, given by R prime of x, is the approximate revenue from the x plus once item. The derivative, R prime of x, is approximately equal to R of x plus 1 minus R of x, or R of x plus 1 is approximately equal to R of x plus R prime of x. And finally, the marginal profit at x given by P prime of x is the approximate profit from the x plus once item. P prime of x is approximately equal to P of x plus 1 minus P of x, or you could say P of x plus 1 is approximately equal to P of x plus P prime of x. Now that's a lot of information in a definition, and you're probably thinking, wow, that's rather wordy, and it is. Let me try to explain what's happening here with a graph on the side. Suppose you are manufacturing a certain number of items, and at some point you manufacture X number, and we don't know what X is. It could be 1,000, it could be 3. But somewhere you will manufacture the X item, and of course the next one you produce will be X plus 1. And that's why you have X and X plus 1 mentioned throughout the definitions, right? We have an X plus 1 here, we have an X here. And of course, if you use algebra to rewrite, you could get C of X plus 1 by itself by adding C of X to both sides. That would give you this. So these are not two different formulas or anything. This is just one rewritten in terms of the other. But anyway, as you create that X item and the next one, X plus 1, that is going to affect your cost, right? Because you're going to have to pay a certain amount to create this item, and the cost to create the X number of items would be C of X. And then when you create the next item, the cost may go up. So we'll put the point here. Theoretically, I suppose the cost could actually go down. And a lot of times the cost does go down as you increase the number of items produced. Now, once you create the next item, again, you have a different cost, and we will denote that as C of X plus 1. So what has happened here? Well, let me change colors, and I will try to illustrate. I'm going to draw a horizontal segment from x to x plus 1. And then I'm going to draw a vertical segment here. So what is the difference between this point here and, say, this point here? Well, if you subtract, you would get a difference of 1. And then, of course, the difference here is going to be c of x plus 1 minus c of x. Because you would take the entire height here, right? That would be c of x plus 1. And then you would have to subtract this height here in order to get the change in x. And you may recall that the rise divided by the run actually gives you what they call the slope of the given line between those 2 points. So here's a line between the 2 points. We have a change in the y value, or the change in cost in this case. And then, of course, we have our change in x, which in this example happens to be 1. The derivative is approximately equal to c of x plus 1 minus c of x. The derivative is approximately equal to this distance here. And we could create the same graph for the marginal revenue and the marginal profit as well. It's the exact same concept. Because as you create one extra item, your revenue changes. As you create one extra item, your profit changes. So hopefully that graph eliminated, I guess, some of the more nebulous concepts mentioned in this definition. It is a wordy definition, but I hope the graph helped. So let's get down to an example here and see if we can't figure out what's going on and apply the definition to some business models. Example 1. Given that c of x is equal to 62x squared plus 27,500, and r of x is equal to x cubed minus 12x squared plus 40x plus 10, find each of the following. A, the total profit, which is P of x. B, the total cost, revenue, and profit from the production and sale of 50 units of the product. And then part C is going to be the new stuff. Find the marginal cost, the marginal revenue, and marginal profit when 50 units are produced and sold. So starting with part A, you may recall that the amount of profit that one makes is going to be the revenue minus the cost. And they simply took the revenue equation and subtracted the cost equation, and the result is P of x. That is the profit function. So that's all they did there. And we've talked about that before. And hopefully by now, this is not a problem for you. Part B says to find the total cost, revenue, and profit from the production and sale of 50 units of the product. All we have to do is go into the cost function and the revenue function and our recently generated profit function, and we substitute in 50. So C of 50 is going to be 62 times 50 squared plus 27,500. And the cost of producing 50 items is going to be 182,500. When they plugged 50 into the revenue equation, they ended up getting $97,010. So this is how much they made when they sold 50 items. And notice that the profit, which is the revenue minus the cost, all they did was they took the $97,010, which is the revenue amount at 50, and they subtracted the cost of producing 50 items, and they actually lost money. That's what that negative sign indicates. Their profit is actually negative $85,490. And on part C, find the marginal cost, marginal revenue, and marginal profit. Now remember that the derivative of the cost function gives you the marginal cost. And if you take the derivative of 62x squared, and so you're going to multiply the 2 times 62, that will give you 124, and then you will have x to the power of 1. And of course, the derivative of a constant is 0, so the derivative of 27,500 zeroes out. So once you take the derivative, just plug in 50 for x, and you will see that the marginal cost is 62,000. What does that mean? It means that once 50 units have been made, the approximate cost of the 51st unit is going to be $6,200. So it's going to cost you $6,200 to make that 51st item. What about the marginal revenue? To get the marginal revenue equation, just take the derivative of the revenue equation. And again, this is just power rule. The derivative of the derivative of x cubed is 3x squared. You're going to subtract from that the derivative of 12x squared, which is 24x. The derivative of 40x is 40, and then the derivative of 10 is 0. And once you get the marginal revenue equation, just plug in 50, and you will see that the marginal revenue is 6,340. And what does that mean? It means that once 50 units have been sold, the approximate revenue from the 51st is 6,340. So this is a good way to tell exactly how much money you're going to make once you make the next item. And finally, we look at the marginal profit. This is derived by taking the derivative of P of X. Again, we plug in 50, and we see that the marginal profit is $140. So let's interpret that. Once 50 units have been produced and sold, the approximate profit from the sale of the 51st item is $140. So let's review that. Once we have produced or sold the 50th item, we can actually tell the cost of making that next item. We can tell the revenue that we will make off of that 51st item, and then we can figure out the profit that we will actually make on the next item. Example 2. Donaldson's milliners produce hats. The cost, C of X, in thousands of dollars to produce X thousand hats, where C of X is equal to 40 minus 18 times e to the power of negative 0.08x, is given. Find the marginal cost when 10,000 hats are produced and estimate the cost of producing 11,000 hats. Keep in mind a couple of things here. First, the cost in thousands of dollars to produce X thousand hats. So when we get to the problem, we're not going to plug in 11,000, right? We're going to plug in just 11 because it's the cost to produce X thousand hats. Just want to make sure that's understood from the very beginning here. Well, here, X is going to equal 10. That represents 10,000 hats. So C of 10, all we have to do is go into the cost equation and plug 10 in. And we can see that it's going to cost about $31,912 because this is 31.912 thousandths. Just multiply this number by 1,000. So that would be the cost of producing 10,000 hats. The derivative of C of x using the chain rule would give us this. If we simplify, we see a much easier version of C prime of x. And then we plug in 10 again, and we can see that the marginal cost when 10,000 hats are produced is about $647. Now, how do we get 647? Because this is 0.647 thousandths, so multiply by 1,000 there. This marginal cost is the approximate additional cost to produce another 1,000 hats. When 10,000 hats have already been produced, thus the estimated cost to produce 11,000 hats is going to be C of 11, which is going to be the cost of the first 10,000 hats plus the change. And that is going to give us 32,559. Okay. Let's move to differentials and delta notation. But before we proceed, I do want to go back and say one thing about C of 11. Could we have plugged in 11 into the cost function? Could we have just plugged in 11 for x? Yes, we could. We could actually plug 11 in, and we would get something very close to this. So keep in mind that what we are doing here is we are estimating the amount to produce, let's say, the next 1,000 hats. And as you can see, if you plug 11 into C of x here, you will get a number very close to 32,559. Okay, so moving on to differentials and delta notation. Now this is where we get into the slope that I mentioned earlier. Notice that we have 2 points on this graph, and I'm going to highlight them here with red X's. We have a point here, we have a point here. And of course, there's a vertical distance between the points, which is the change in y, and then there's a horizontal distance between the points, which is the change in x. And here we decided to call the change in x h. That just makes it a lot easier to write. And of course, the change in y can be expressed as f of x plus h minus f of x. Now, why is that? Let's go back and clear this off. We know that this entire length here is f of x. And this entire length from here to here that I'm highlighting in green is, I'm sorry, the red line is actually f of x plus h, and the green line represents f of x. And if you subtract the length of the red segment, if you subtract the length of the green segment from the length of the red segment, you will generate this length right here, which is the vertical displacement. And that's just f of x plus h minus f of x. Let me just put this in a simpler context. Suppose you know that you have a point located here. And let's say this point is 1 foot off the ground. And then we have a point here that happens to be 3 feet off the ground. Well, what would be the distance, the vertical distance between the 2 points? In other words, what is the length of this red segment here? Well, wouldn't it be 3, which is the entire length from the x-axis to the 3? But then you would have to subtract this length here. In other words, it would be f of x plus h minus f of x. That would be the difference. And then you would have to divide by this displacement here. And that would give you the slope of the line that goes between these 2 points. So let's take a look at an example. It says to find delta y in each case. Before we start, let's go back and look at what delta y represents. If you go back to this picture, delta y just represents f of x plus h minus f of x. So looking at example 3, part A, we have y is equal to x squared. We start off when x is equal to 4, and then we move slightly to the right, 0.1. So what might that look like? Well, let's see. Here x is at 4. And if we move over slightly, I'm going to exaggerate this so that you can see what's going on. So this is not to scale. But if we move over to the right, 0.1, that distance is 0.1. Isn't it true that this x value directly under the end of the segment would have to be located at 4 plus 0.1, which is 4.1? So there, that is your change in x. There you have your delta x. So how do we get the y values? Well, if we plug 4.1 in for x, we get 4.1 squared, which is 16.81. So the y value, and again, this is not drawn to scale. If x is 4.1, if we plug that into the equation y equals x squared, we would go all the way up here where y is equal to 16.81. And if we plug 4 in, of course, 4 squared is 16. So we'll put that here. Now, we're looking for the change in y, which is just the vertical displacement. In other words, we are looking for the length of this segment here. Well, isn't the length of that segment going to be 16.81 minus this length here, which is 16? So the change in y is actually 0.81. Part B, we have y is equal to x cubed. This time we start at 2, but we're going back 1/10. We're moving back 1/10. But it's the exact same formula, right? Delta y is f of x plus h minus f of x. This time, instead of adding 1/10, we subtract 1/10 because that is the change in x. Minus f of 2. And if we do the math, we get down to negative 1.141. So let's draw a picture of that. What might this look like? And again, this is not drawn to scale. Let's put 2 here. And this time we're going to have to move to the left 1/10 So if we move to the left, this is the change in x, right? That would be 1/10 moving to the left. Well, 2 minus 1/10 is 1.9. So we would be at 1.9 here. And at this point, I need to plug these x values into y. And 1.9 cubed is 6.859. So the y value here would be about 6.859. And if we plug in 2 for x, 2 cubed is 8. So that point would be here, which is 8 units up. And notice I get a right triangle. And all we're really looking for here is what is the length, what is the vertical displacement there? Well, the vertical displacement is going to be 6.859 minus 8. Why do we have to do it in that order? Because we're starting high, right? We're starting at 2, and we're moving to the left, which means this point here is P1, because we start here, and once we move to the left, we end up at point 2. This is the second position. And notice that we have a drop, right? We actually drop down as we move to the left. Since we drop down as we move to the left, that gives us a negative value. And here we have another definition. For f, a continuous function that happens to be differentiable, and if you have a small change in x, the derivative is approximately equal to the slope. In other words, delta y over delta x. The change in y over the change in x. Some of you may remember from high school the teacher saying rise over run. That quotient, that fraction, is approximately equal to the derivative if you have a very small change in x. If you have a large change in x, you will definitely lose accuracy. And finally, if y is equal to f of x, we define d of x, or dx, called the differential of x, by dx is approximately delta x, and dy, called the differential of y, is approximately equal to the derivative f prime of x. Let's look at this picture below. Notice we have several points here. I'm going to highlight the first one in green here. And here's the second point in green. And notice that as we move horizontally some increment of x, that's our delta x, which is equal to our differential of x. Notice that we have a vertical drop here. If we were to look at this tangent line to this point, notice how we have a tangent line drawn to this point here. And we said before that the slope of the tangent line is the derivative. But we could also approximate that by finding the slope of this secant line that goes through the 2 points. In fact, in algebra, that's exactly what you did. You found the slope of the secant line, which is the rise over the run. But notice that the slopes of the two lines are fairly close. They're barely off. In fact, the difference between the two is only this little amount here. So that's where this definition comes from. Now, some of you may be struggling with this and thinking, okay, this makes no sense. And that's okay. You really do not have to fully understand that. It would be nice if you did. I do not really understand how my cell phone works, but I do like it and I can use it to my advantage. But if you understand the formulas, if you can at least apply these formulas, you will be okay for this course. Let's take a look at some examples here, at least one example. Example 4. Example 4 says to consider the function given by y is equal to the square root of x. Find dy when x is equal to 9 and dx is equal to 1. Part B says use the result from part A to estimate the square root of 10. And then finally, find the difference between the approximation found in part B and the actual value of the square root of 10. Okay. Let's see what the square root of x looks like. Let me see if I can't sketch this. If you want to, you can put it in Desmos. You would get a far more accurate graph than what I'm about to show here. But suppose this is the y-axis. Here comes the x-axis. The square root of x looks something like this. The square root of 0 is 0. The square root of, let's say, 4 is 2. And the square root of 16 is 4, and so on. It would look something like this. That's what a graph of the square root function looks like, generally speaking. So part A says, find dy if x is 9 and dx is 1. Well, remember that dy over dx, is just the derivative with respect to x. So what are we going to take the derivative of? Well, our function is y is equal to the square root of x, and we can write that as y is equal to x to the power of 1/2. Remember, the square root of x is also x to the power of 1/2. If this had been the cube root of x, then we would say x to the power of 1/3. But anyway, if we take the derivative using the power rule, we would get 1/2 times x to the power of negative 1/2. And of course, we can take that negative 1/2 to the denominator and rewrite it as a square root, and that would give us dy is equal to 1 over 2 on the square root of x times dx. If you want to know dy when x is equal to 9 and dx is equal to 1, just plug in 1 for dx, plug in 9 for x, and you can estimate dy to be about 1/6, to be equal to 1/6, which is approximately 0.16 repeating. So there is dy. Let's look at part B. We figured out that dy we know that dy is equal to approximately the square root of 10 minus the square root of 9. And the square root of 10 is approximately equal to the square root of 9 plus dy. Now, how did we get that? Well, we just got the square root of 10 by itself on the right side. We added the square root of 9, which is 3. We just added that to both sides. So the square root of 10 is approximately equal to the square root of 9 plus dy. And we figured out that dy is 1/6. And if we add those together, we can see that the square root of 10 is approximately 3.16 repeating. If we use a calculator and type in the square root of 10, we get 3.16227766, which is very close. So by using this estimation, we actually get a difference of only 4 thousandths there. So let's sort of look at this in a graph. Remember we said that if you graph the square root function, it looks something like this. And we're looking at x is 9. And we know that the square root of 9 is 3, so that would be 3 for the height there. So this point here is located at 9, 3. And then we wanted to estimate the square root of 10. Well, if x is 10, then this point here would be located at the square root of 10. But we wanted to figure out an approximation for that. Well, we figured out, remember, we know that dy is going to be approximately this drop here. It's going to be the square root of 10 minus the square root of 9, which is 3. So this is our dy. This is our change in y. And if dy is approximately equal to the square root of 10 minus the square root of 9, or 3, if I add 3 to both sides, then I know that dy plus 3 is approximately equal to the square root of 10. And luckily, we were able to estimate dy, and we got 1/6. So 1/6 plus 3 is a very good approximation for the square root of 10. Not 10, square root of 10. So I hope that diagram helped. I do apologize for the legibility, the handwriting here, trying to use technology. But think about it and do some practice with these types of problems, and hopefully it will make more sense to you. And finally, let's look at example 5, looking at cost and tolerance. In preparation for laying new tile, Michelle measures the floor of a banquet hall and finds it to be square, measuring 100 feet by 100 feet. Suppose these measurements are accurate within 6 inches, either way. Use a differential to estimate the difference in area due to the tolerance. That's part A. Part B says to compare the results from part A with the actual difference in area, delta A. If each tile covers 1 square foot and a box of 12 tiles costs $24, how many extra boxes of tiles should Michelle buy for covering the floor? And what is the extra cost? Well, let's start with part A here. We know the floor is square. So here's our square floor. And she figured out that it's a 100 by 100 in terms of feet. So we have 100 feet here and 100 feet here. And we figured out that her measurements are accurate within plus or minus 6 inches. That's half of a foot. Remember, we need to be in the same units of measure. And since we have 100 feet by 100 feet, we're going to change that 6 inches to 0.5, 1/2 of a foot. That way we keep the units the same. As a reminder, the floor is a square, and the measurement is presumed to be 100 feet per side with a tolerance of about 1/2 of a foot either way. What does that mean to us? That means that she could have measured it 1/2 of a foot too little, or she may have gone 1/2 of a foot too far out. In other words, we have some tolerance here. We know that the area of a square is x squared. And if you take the derivative of that area function with respect to our variable x, the derivative of x squared is 2x. And if we solve for dA, all we have to do is just cross multiply here. dA times 1 is dA. We can see that our differential on A is actually 2x times dx, where dx represents our differential on x. So we have figured out dA in terms of x. Now it says find dA if x is 100 and dx, which is our tolerance, is plus or minus 1/2 of a foot. Well, to do that, we will substitute in our x value, and we said x is the length of one side. So we would have to plug in 100 here for x. And we know that the tolerance either way on the measurement, right, is going to be plus or minus a foot. I'm sorry, 1/2 of a foot, 0.5. And if we multiply 2 times 100, we get 200. And then 200 times 1/2 is 100. So we are going to be off. We could be off by as much as 100 square feet either way. And that sounds like a lot to me. In fact, I guess the author agrees, because the author says a small error in measurement can lead to a significant difference in the resulting area. So she estimated about 100 by 100 feet. And if we gave her 1/2 of a foot in either direction, if we gave her that tolerance level, then the difference in the area could actually be 100 square feet either way. Part B says, compare the result from Part A to the actual difference in the area. To find the actual difference in the area, what we have to do is, it says, let's see, if the true length is at the low end, then we have 99.5. In other words, if she measured it, if she underestimated it by half of a foot, then the area of the square would be 99.5 by 99.5. And if you want to know the difference between a perfect 100 by 100 and a 99.5 by 99.5, you just subtract the areas. That gives us negative 99.75 square feet. So if she underestimated this, then she lost 99.75 square feet. But what if the measurement happened to be closer to the upper end? 100 feet plus half of a foot. Well, take the area of a 100.5 by 100.5 square, subtract from that the estimated amount, which was 100 by 100, and at the high end, she would have 100.25 square feet. So let's sum that up. What does that mean? We see that delta A, the actual difference in area, can range anywhere from negative 99.75 square feet to 100.25 square feet. Both values compare well with the approximate area of plus or minus 100 square feet. And I will leave part C for you here. This is where we're just trying to figure out the difference in cost based on the amount of error. And here we have another definition. It says to let y equal a function of x, let it be differentiable at x is equal to a. The linearization of the function at x is equal to a is given by f of a plus f prime of a times x minus a. And again, this is just mimicking the slope. So we have a point here at x is equal to a, and we can take the derivative of this tangent line. That would be f prime of a and notice it says for x values close to a, the difference between L of x and f of x is very small. In fact, the difference between L of x and f of x is, here it's easier to see because the tangent line is higher. But notice that as we get closer to x, the difference between the tangent line and f of x is actually very small. And that's where this equation here comes from. Let's take a look at an example. Example 6. We're looking for the linearization of f of x as the cube root of x when a is equal to 8, and use it to approximate the cube root of 9. Well, here our a value is 8. They give us that. And if we plug 8 into the function, we figure out that we have the cube root of 8, which happens to be 2. That's a nice, easy number. If you take the derivative of the cube root of x, which is x to the power of 1/3, using the power rule, we end up getting, once simplified, we end up getting 1/3 on the cube root of x squared. And then we can find the derivative at 8. That would be the slope of the tangent line when x is equal to 8, and the derivative is going to be 1/12. And then we can just apply the formula. The formula says that y is equal to f of a plus f prime of a multiplied by x minus a. And we would just plug in our values. Again, f of 8 ended up being 2. If we plug 8 into the derivative, we end up getting 1/12 for the derivative at a, and then we look at x minus a. In this case, x minus 8. And all they did was algebra. They just distributed the 1/12 across, and we ended up getting this equation here for y. Notice that the slope of the line is 1/12, which should not be a big surprise because that's the derivative. And here the y-intercept ends up being 4/3. The graphs of the cube root of x and the line LX, L of x, which is 1/12 x plus 4/3, are shown. So if we look at this curve here, this is part of the function cube root of x here. And then we figured out that the equation of this line happens to be 1/12 x plus 4/3. But notice that as you get near 8, here's where x is equal to 8. The closer we get to 8, we can see that there's a slight difference between the line and the curve. Therefore, we can actually approximate L of 9. So if we plug in 9 into the line function, we end up getting 2 and 1/12. So we know that the cube root of 9 is very close to 2 and 1/12 because the line is very close to the curve. I'm going to draw somewhat exaggerated here. We have the curve, which is the square of the cube root of x. And then we have figured out the equation of the line that touches when x is 8. If we plug 9 in, we can figure out this height. We can plug that straight into the linearization function. In other words, we can figure out how high this thing goes by plugging it in. And that's exactly what they did in this problem. They plugged 9 straight into L. And they know that the cube root of 9 has to be this height here. And they're very close. They're only off by this little amount here that I'm going to mark with X. So we will accept that little bit of error if we have to. So this includes section 3.6, and now we will talk about section 3.8. Section 3.8 is on implicit differentiation and logarithmic differentiation. And implicit differentiation is probably my favorite because the algebra is usually not too bad. And this allows us to find the derivatives of things that are not functions. For example, suppose we have a circle. A circle is not a function because a circle fails the vertical line test, right? Remember, in order to be a function, if you drop a vertical line across a function, it can only touch the function at most one time. But with a circle, the vertical line actually hits it twice. So with things like circles and ovals, hyperbolas, those types of things, those are not functions. But fortunately, with the use of implicit differentiation, we can find derivatives at given points on circles and things of that nature. Now, what makes it impossible to find the derivative without implicit differentiation? Let's look at an example. If I had asked you previously this semester to tell me the slope of the tangent line when x is equal to 3. So here, let's say x is equal to 3. Well, the problem is there are actually 2 points on the circle where x is equal to 3. There's a point here where x is equal to 3, and straight above where x is equal to 3. So there is no one derivative for x is equal to 3 because you would have a tangent line here that has a slope, and you have one directly beneath, that one has a slope. But implicit differentiation allows us to pinpoint exactly which point we're talking about because we use not only the x value, we use the y value as well. That tells us exactly which point we're talking about. Now, rather than go through the center page and read all of this to you, I don't want to insult your intelligence. I know you can read. So I will let you read this. I want to go straight to the example. I want to go ahead and just go straight to example number 1. Example number 1 says that we have y cubed plus x squared times y to the power 5 minus x to the power 4 is equal to negative 11. This would be very difficult for us to graph. In fact, I'm not even going to try to sketch what this might look like. If you have some sophisticated software, you might be able to graph this. Desmos, as far as I know, cannot handle it, and the TI-84 would not be able to do this. Now, if you know a way to graph these using Desmos or the TI-84, by all means, feel free to let me know. I have not figured out how to do that, but that's not really the point of this exercise. The point here is, if given this type of a situation, if given this type of a graph, I can't say function, but given this type of an expression, could I find the derivative using implicit differentiation? And the answer is yes. We can't forget the chain rule. The chain rule is back in full force here because these y's here represent a function. These are functions raised to a power. And we have to keep that in mind as we take the derivative. So part A says find dy over dx, find the derivative of y with respect to x using implicit differentiation, and then find the slope of the tangent line to the curve at the point 2, 1. Okay, let's go ahead and move on to the next page and we'll take a look at this. By the way, the picture is shown about the middle of the page on the right. Let me talk about that very quickly here. Notice that this picture is not a function because if I drop a vertical line, it looks to me like it might pass through more than once. It may be a stretch, but I'm not really sure. It looks to me like this would not be a function. And let's see what we can do with the derivative here. Notice that we simply take the derivative of both sides of the equation with respect to x. We typically don't write that step. We usually go straight, into the derivative. And if you can sort of think about distributing this d over dx all the way across here, that would give us this step. So far, nothing really enlightening, except they figured out that the derivative of negative 11 is 0, because negative 11 is a constant. Now for the good stuff right here. What did they do? Well, they did the power rule. They took the derivative of y to the power of 3 with respect to x. Remember that y is a function raised to a power. So it's going to be power rule, 3y squared, but you have to do times dy over dx. Same thing with the second term here. This time they had to use the product rule. So they took the first one times the derivative of the second one. The derivative of y to the power of 5 is 5y dy dx. Plus the second times the derivative of the first. The derivative of x squared is 2x. And then, of course, the derivative with respect to x of x to the power of 4 is going to give us 4x to the power of 3. So this is the extended rule here. And now we simply have to solve for dy over dx. Notice that we have a dy over dx here. We have a dy over dx here. And therefore, since dy over dx is in both terms, we can factor out dy over dx, which leaves us this in parentheses. The right side is unchanged. Then we can just get dy over dx by itself by dividing both sides by 3y squared plus 5x squared y to the fourth. So dy over dx is actually this expression here. Now we can figure the slope at the point 2, 1. All we have to do is go back into dy over dx, and we will plug in 2 for x and 1 for y, and we can see that the slope is 28 over 3. So the slope of this line here at 2, 1 is 28 over 3. So let me stop here and do a problem similar to this. Suppose I have a circle, x squared plus y squared is equal to 1. We'll just do the basic circle here. Now this circle happens to have the center at the origin. It happens to have a radius of 1. So I'm going to draw it. Let's just say it looks like this. And I want to know the derivative of at any point on the circle, whether it's this point here or this point here. It doesn't really matter. Maybe this point directly below the first one. I want to know what is the derivative at any of these points. Well, again, circle is not a function. We can imply functions in here, and we're not going to get into that. That would be something that we would do if this were a course for math majors. But we're going to have to keep in mind that this y here does represent implied functions, various implied functions. So all I have to do is just take the derivative of every term. I'm going to take the derivative of x squared, which is 2x, plus I'm going to take the derivative of y squared with respect to x, and that's going to be 2y prime. Now the author used dy over dx instead of y prime. I prefer using y prime. So 2x plus 2y y prime would be equal to, I have to take the derivative of the 1, which is 0, and then I need to get y prime by itself. So that's going to give me 2y prime is equal to negative 2x. And if I divide both sides by 2y, that gives me negative x over y. So you tell me what the coordinates are for any point on this circle. I will plug those in here, and I can tell you the slope of the tangent line at that given point. So hopefully using the circle helped you to better understand this example here. Again, I tend not to do dy over dx. To me, it's just extra notation. I just prefer to use y prime, and you may do that as well. Example 2, exact same type of thing here. We've got, so this time we have a square root function, and they want us to find the derivative of p with respect to x. And all they did was they first took the derivative on both sides with respect to x. And the derivative of x with respect to x is 1. And then, of course, the square root can be written as, in this case, 200 minus p to the power of 3 raised to the power of 1/2, right? Since it's a square root, and then once you take the derivative, 1/2 minus 1 is negative 1/2. But then you have to take the derivative, or in this case, I would just say p prime, dp over dx. Where did this come from here? Well, this is chain rule, right? Because we have a function here raised to a power. And once they simplify, they see that they can figure out dp over dx by getting dp over dx by itself. We can also apply implicit differentiation to logarithms, and hopefully you have not forgotten the rules for differentiating logarithms. But let's look at an example here. Let's look at example 3. And of course, they had to start off with something somewhat complicated, but that's okay. Here we have y is equal to all of this, right? We have a polynomial raised to the power of 3. We multiply that by the square root of this polynomial here, which is quite a lot to look at. And, you know, we want to know, what is y prime? What is dy over dx? The first thing they did was they took the natural log of both sides. Why would they do that? Well, if you tried to find the derivative of y with respect to x using the product rule, you would find yourself in the middle of an algebraic nightmare. That would be quite a bit to deal with, perhaps. Maybe not in this particular problem, but if we had more expressions involved, we could get bogged down in some very heavy algebra. So we can use natural logs to make this a little simpler, because we know that the natural log of a product is the sum of the logs. Remember that if you take the natural log of m times n, you can break that apart as the natural log of m plus the natural log of n. And that's exactly what they did. They introduced the natural log on both sides, and then they used that property here, and they separated the product into the sum of two logs. Oh, here it is, right here. They used that property. Here they just used the property, here they used the property that says if you take the natural log of a to the power of k, it's the same thing as k times the natural log of a. In other words, they brought this 3 here, this exponent, down to the front. And over here, they brought the 1/2 down to the front. That's just another one of our log properties. And that puts us in this situation here. And then finally, we take the derivative with respect to x. We take the derivative of both sides with respect to x. So what does that look like? Well, remember, the derivative of a natural log of y is the derivative of y with respect to y, 1 over y, and y prime. You may remember I probably said it this way, that the derivative of u, where u is a function of x, is du over u. So if you take the derivative of the natural log of y, it's going to be dy over y. If you don't remember that, Go back and review the derivatives for natural logs. But anyway, the derivative of ln y is dy over y. And we can't forget the dy over dx, or the y prime, right? So 1 over y prime, that's the derivative on the left side. And then they take the derivative of all of these. So how did they get 4x cubed plus 3 over x to the power of 4 plus 3x minus 1? Well, remember, the derivative of the natural log of u is du over u. Well, here, u is equal to x to the power of 4 plus 3x minus 1, and the derivative of that would give you 4x cubed plus 3. This 3 here is just carried down from the previous line, right? It came from here. So here's the du, and here's the u. So that derivative would be du over u. And they did the same thing here. The derivative of this u is going to be negative 15x to the power of 4. This is just power rule, so du over u itself. And the 1/2 just came along for the ride. So that leaves us 1 over y prime, is equal to all of this here. They just distributed the 3 across on the first term and got the 12x cubed plus 9. And then they just kept the 2 here on the bottom. No big deal. Remember, our goal is to ultimately get y prime or dy over dx by itself. And they just multiply both sides by y to do that. Once you multiply both sides by y, those y's cancel. That leaves you dy over dx. And at this point, we are finished. Now, you may be asking yourself, what happened to this y? Well, if you go to the very beginning, y is equal to all of this, right? So they just substituted that back in, and that gives us the entire answer in terms of x, which is our goal. Okay. I will let you, at this point, I'm going to let you study this section here on your own. This is x to the power of x, which is a very interesting graph. It has very interesting properties. I will let you read through this, but I want to work something sort of on the side here. I want to give us a problem to work just to get some extra practice. Suppose I have this. Suppose I have 3x y plus 2y squared minus 1 is equal to x. I have no idea what this graph looks like, but I do want to find y prime. I want to figure out what is the derivative of y with respect to x. So here we go. I'm going to take the derivative of the first term, then I'm going to take the derivative of the second term and the third term, and then finally I'll take the derivative of x. Well, this is a product here. I have 3x. I'm going to group that together as one thing. I'm going to multiply, I'm going to find the derivative of 3xy. I'm going to take the first function, 3x, times the derivative of the second function, which is the derivative of y with respect to x, which is y prime. Again, I like to use y prime instead of dy over dx. So I took the first term times the derivative of the second, plus the second term, which is y, times the derivative of the first. That's going to be 3. So I have 3x y prime plus 3y. Now I have to take the derivative of the second term. The derivative of 2y squared, remember y is a function, that's going to be 4y y prime. That has to do with chain rule. And then the derivative of -1 is 0, and the derivative of x with respect to x is just 1. Now I'm going to take everything that has a y prime, I'm going to leave it on the left side, and I'll flush all of the other terms to the right side. So that's going to leave me 3x y prime plus 4y y prime would be equal to 1 minus 3y. Again, everything that has a y prime goes to one side, all of the other terms go to the opposite side. This allows me to factor out a y prime. So that leaves me with y prime, open parentheses, 3x plus 4y. Is equal to 1 minus 3y. All I did was factor out the y prime. Now to get y prime by itself, that leaves me 1 minus 3y over 3x plus 4y. So you tell me the x and y value, and I will tell you the derivative at the point xy. So this is dy over dx. Let's do one more. Four x squared plus y cubed is equal to 4. Again, we just take the derivative of each term. The derivative of 4x squared with respect to x is going to be 8x. The derivative of y cubed is going to be 3y squared, which is just power rule, but I have to multiply that by y prime. And the derivative of 4 is 0. So that's going to give me y prime is equal to negative 8x divided by 3y squared. Again, you tell me x and y, I'll plug those values in, and I can tell you the slope of the tangent line or the derivative at that particular point. Now, why do we have to do this extra step? I keep saying chain rule. Keep this in mind. If you're looking for the derivative of y with respect to x, if y is written in terms of if y is another function, and let's say that u is a function of y, then you would have to take the derivative of u. I'm sorry, you'd have to take the derivative of y with respect to u, and you would have to multiply by the derivative of u with respect to x in order to figure out dy over dx, because these would essentially cancel out. Now, some of you may not get that, some of you may not care to get that, but as long as you can go through the mechanics of implicit differentiation, you should be okay. Thank you.